All right, welcome everybody who's joining us live or listening to this recording in the future. I'm Amelia Chapman, and I'm welcoming you to this training for Museum and Informal Education Alliance and NASA's Solar System Ambassadors. Thanks for being here today. Just a bit of housekeeping, as I mentioned, please make sure your camera's off unless you're one of our speakers. And if you accidentally unmute yourself, I will find you. I'm going to turn it over to Dr. Saladino, who will give our introductions.
Thank you very much, Amelia. Phil, sorry, can we have Tom the first slide?
You can
Okay.
see that okay? Yes.
No, I cannot see anything.
Oh, must have stopped sharing. 1 second. Sorry.
No worries. Thank you very much. There we are. I can see the slides now. So, hello everyone. My name is Marta Irene Saladino. I work at the Space Telescope Science Institute, and I'm here today with NASA's Universe of Learning. So, I want to welcome you all to today's briefing. It's called The Shocking Universe, and we're going to learn a lot of different things. For people who are watching us in the future, welcome. We have a very nice lineup of speakers today. I encourage you all to please look at their bios on our website. Our first speaker is going to be Dr. Tom Ray. He is at the Dublin Institute for Advanced Studies, and he's going to be telling us about star formation. Can we move to the second slide, please? Thank you. Our second speaker is going to be Dr. Roger Romani. He's going to be talking about shocks in stars. And our third speaker is going to be Dr. Philip Appleton from Caltech. He's going to be talking about shocks in Stefan's quintet. At the end, we're going to have some time for questions and answers. If you have any questions, please feel free to drop them in the chat or wait, please, until the end of the session so you can have your answers to your questions. And then I'm going to be sharing some resources. So let's get started. Tom, the floor is yours.
Oh, good evening, everybody. So my name is Tom Ray. As was mentioned, I'm from the Dublin Institute for Advanced Studies. Now that's Dublin in Ireland, by the way. I mean, I know there's a Dublin in Texas and a few other places, but it's Dublin in Ireland we're talking about here. And I'm going to tell you about shocks in star formation. But first, because I am the first speaker, I'm going to tell you a little bit about shocks in general and then move on to the star formation process itself. So, what is a shock? Well, if you have something like a gas or even solid or whatever moving, faster than the speed of sound in that gas, for example, then you usually end up with shocks. And this is an example here where there's a jet engine being tested by NASA. It's called a J58 engine. And anyway, you can see in the trail of the engine here a series of shocks. So you may have seen some images of airplanes traveling supersonically and the shocks that they produce, or you may have heard the supersonic shocks. But the basic point is if you have something traveling faster than the speed of sound, then shocks will form. So let me show you an example. This is a picture of a bullet. And bullets travel through air and they're traveling faster than the speed of sound in air. And as a result, they form a shock. And you can see a shock here called the bow shock in the front. And Roger will tell you more about bow shocks in a little while. But you see the bullet here, and then there's a series of secondary shocks as well that form. The essential point is this is traveling faster than the speed of sound in air. And on this side, it's normal density of the air, but on the, if you like, the side of the bullet, the air density increases. And that's a feature of a shock. you actually get changes in density, you get changes in velocity, and also on other things like the sound speed itself and the temperature. But you don't have to go very far to see a shock. Here's an example, something you could see every second day. This is actually just a common sink. You have the water flowing down from the faucet into the sink, and as a result of the change in the speed of the water, initially when it comes from the sink, or sorry, from the faucet, it's traveling at high velocity, and then it's slowed down within the sink itself, and so you get a fast flow changing into a slow flow. And you may have seen this occasionally in your own sink when you let water flow into it. But you might also notice the next time you see it that this side is actually a little bit thicker. That's because a little bit higher in the sink. And that's because the water is flowing more slowly, and so there's a buildup of matter. So, okay, so that's a very brief introduction to shocks, and you'll hear more about them later on. But now let's turn to star formation. So, some of you may have gone out on a very dark night, looked at the Milky Way, and you would notice in the Milky Way very clearly a number of holes, dark areas like this. And those dark areas are not places where there's an absence of stars. What's essentially happening is that in those areas, which are full of gas and dust, stars are actually forming. So, perhaps some of you remember your Shakespeare, and they talked about constancy of the stars in Julius Caesar. Well, the stars aren't constant, they're evolving all the time. And a star typically takes about 1 million years or so to form, but 1 million years, you've got to compare that with how old, for example, our sun is, which is about 5,000 roughly million years. And of course, the sun will last another 5,000 million years. So we're really talking about infant stars here when we talk about stars that are only 1 million years old. And the basic process is illustrated here. You start off with a cloud, which is about 3 or 4 light years apart, to give you an idea of those dimensions. If you compare it with the distance between the sun and the earth, which is 93 million miles, you're talking about a size here of about 200,000 times bigger than the distance from the Earth to the Sun. And the cloud then is very tenuous, but it starts to collapse. It's actually spinning as it collapses, and of course, like a skater, when a skater pulls in her arms, she spins up. In the same way, the cloud starts to spin up, and it forms a disk, and that disk in turn forms planets. And we now know that roughly half of the stars you see in the night sky are surrounded by planetary systems. So remember that the next time you look up at the night sky. And here's a typical cloud. So as I said, it's not a hole in space that might look like one, but basically it is blocking all of the stars that are behind. And it's something like this which will actually collapse to form a star like our sun. And to illustrate that there's a lot of gas and dust here, here we have the Hubble image of what has been called the pillars of creation. It's a region where new stars are forming inside these pillars. Here's an actual image by the mid-infrared instrument, which I was involved in building for the James Webb Space Telescope. And when you switch to the infrared, which is longer wavelengths, you can actually penetrate the cloud much more, rather like penetrating through fog. And you can start to see many of the stars that are behind the pillars themselves, whereas in this HST image, they're blocked. So we start to see through the dust and the gas that's there. And it's that gas and dust that collapses and forms new stars. And here's an example of a relatively nearby star that's forming. And in this case, we have a disk as well, but the disk is nearly edge on. And this is the disk, which is roughly, we're talking about dimensions comparable to the solar system itself. So this disk will eventually settle into a planetary system. But you'll also notice as well that apart from this scattered light, there's gas going upwards and downwards as well. And this was a real surprise many years ago when we started to study star formation. What we realized was not only, as you can imagine, gas is falling inwards to form a star, but a lot of the gas, something like 10% or so, is actually ejected. And that gas is ejected supersonically. And so here we see shocks. I'll show you an image of more shocks in a few moments. But the basic point is that even when our sun formed 5,000 million years ago, it would have had a jet like this pointing in both directions and stretching for many, many light years. And here's an example. Here we're looking in the infrared and molecular hydrogen. This is taken by the telescope of the European Southern Observatory. The dark area here is where a new star is forming. So even in the near infrared, we can't actually see the new star. Why? It is obscured with gas and dust, but this system is actually extremely young. We estimate it's only 10,000 years old, and which is nothing for a star, of course. But also what you're seeing out here and here are jets of material moving at around 100 kilometers per second, and inside those jets, rather like the jet engine I showed you earlier on, you can see actual shocks forming. But I want you just to hold that image for a few moments, because I'm going to compare it with an image that we took just 2 years back of the same object. So this image was taken from the ground using an 8-meter mirror, so a very big telescope on the ground. But in space, with the James Webb Space Telescope, we were able to essentially replicate these observations. And just to show you what it looks like, when we switch to the James Webb Space Telescope, that's what we see. So, I mean, incredibly more detail. You can see lots and lots of shocks in this system. And as I said, it's about 10,000 years old. So really is an infant system. And one of the first things we discovered with the James Webb Space Telescope is that these jets from a star, when it forms, are almost entirely made up of molecular material. So it's just molecules of gas moving outwards from the star as it forms in this dark lane here in the middle. And in fact, if I go back and forth between the two images, because they are roughly over, 2 decades apart in time, you can see an actual motion. Because we can actually see in the sky, and we've new James Webb Space Telescope images that show this, we can actually see the gas moving outwards, as I said, around 100 kilometers per second. So these are examples of shocks that occur in the process of star formation, and they certainly continue for up to 1 million years. But of course, shocks occur at other stages, not only as stellar birth, but as some of you may know, at stellar death as well, for example, in supernovae. So at that point, I'll finish and I'll hand over to Roger, if I may.
Thank
Do
you,
that.
Tom.
Yeah. So I'll just stop sharing.
Okay, thanks, Tom. Let me see if
There
I
you
can
go.
start my share. How's that look? Can you see it?
We can see it. Thank you.
Excellent. So, thanks for that introduction, Tom. I'm going to tell you a few more words about a particular kind of shock, a bow shock, as was mentioned earlier. Now, let's see if I can get the thing to advance. There we go. So the first thing to note is, as already described, shock waves occur when you have an object that's moving supersonically, faster than the speed of a sound wave, we would say. But a sound wave can be also, as Tom mentioned, a surface wave on water, any kind of wave that's carrying information. If your object is moving faster than that, you will have a shock wave. So these objects that I'm going to be describing to you today are called bow shocks. Now, I want to emphasize that if you get online and you Google this stuff, sometimes you'll see videos which talk about bow shocks. There's no such thing. The analogy here is the bow wave of a boat. So these are properly called bow shocks, not bow shocks. So on the right, you can see a picture of a boat moving faster than the local speed of the water waves on the surface. And you can note that ahead of that, there's going to be a region where there's undisturbed water. That would be the undisturbed medium up front. And then behind that arc-shaped region, which is the bow shock, there is disturbed, shocked, turbulent water. Now, in an astrophysical context, we should keep in mind that in most cases, the objects that are moving through space are relatively small. You know, the size of a planet or maybe a star. That's small on the scale of the interstellar medium or intergalactic medium. So typically what you get is, instead of the physical object itself making the shock, you have a gas around that object, a wind typically, or sometimes a magnetic field. That's actually the object that's providing the shock against the ISM. So to give you some context, let me mention shocks on three different scales. First, on the planetary scale, we know that in our own solar system, a great example is the bow shock that forms around the Earth's magnetosphere. So in this case, the object that's slamming into the wind that's coming off of the sun is actually the magnetic field of the Earth, which makes in its dipole pattern a kind of a structure that is larger than the Earth's radius itself. So in this case, the medium that is being shocked is the so-called solar wind, and it shocks against this magnetic field that stands it off from the Earth, and you get this kind of bow wave arc-shaped structure. On a larger scale, we've already heard about stellar shocks, and a stellar bow shock can occur when you have a stellar wind, and if the star is moving faster than the speed of sound through the interstellar medium, you'll get a shock wave. And remember the speed, well, I should tell you that the speed of sound in the interstellar medium is a few kilometers a second. It does depend on the local temperature, but that's the characteristic scale. So if you have a relatively rapidly moving star with a wind coming off of it, it can make these beautiful arc-shaped shock waves. Here's a couple of examples seen in visible light. Now, on the larger scales, you can get this as well. Galaxies, which we'll be hearing about later, can produce shock waves. And I think a good example of a bow shock is this famous object called the bullet cluster. This is actually two clusters of galaxies crashing through each other. You should really think of a large cluster of galaxies which had a small cluster fall into it and crash through. That's what the image that you see here shows. It's a composite image, a composite of a background of an optical image where you can see the stars, and indeed these little fuzzy things are the galaxies themselves. Superimposed on that in red, or pink, I guess I should say, is an image of hot glowing X-ray gas. Shock waves in general heat material up and cause them to radiate light. That's why we take photographs of them, and that's why they look beautiful. In this case, the X-ray gas, you can see there's two components. There's first the X-ray gas of the original big cluster, and then a bow shock from the X-ray gas associated with the emission from the smaller cluster. The little dots inside of that are the actual galaxies. Now, what makes this image particularly famous is a third ingredient, which doesn't really directly involve us today, but I might as well mention that. In blue, you can see a map of the mass that's associated with these two clusters of galaxies. That map is actually dominated by dark matter, and dark matter does not make a shock wave because sound waves don't propagate within it. And so you can see the two clumps of dark matter have flown right through each other. On the original big cluster of galaxies is the dark matter clump in blue on the left, and the small clump of galaxies is the dark matter cluster on the right. The gas, which does collide and shock, gets left behind, and hence we get this very nice arc of a bow shock of gas heated to X-ray temperatures. Okay, that's all preamble. What I want to now emphasize is that to make one of these bow shocks, you need two ingredients. You need a thing that's moving really fast, faster than the speed of sound. And also, given that astrophysical objects are small, to make a bow shock that's big enough to be interesting and visible, you typically need a strong wind. And that turns me to a class of objects that I and my own research group focus on called pulsars. These are rapidly spinning neutron stars, and I think they're great examples of systems that can make bow shocks. First of all, we know they move really fast, hundreds of kilometers a second. Typically, this seems to be a recoil event from the supernova explosion that formed these. These neutron stars are the collapsed cores of massive stars left behind after a supernova. Now, flying along at hundreds of kilometers a second, it turns out that they also emit very strong winds. As they spin, rotating rapidly, they emit a wind of plasma, a plasma that's made up of electrons and positrons and embedded magnetic field. And that wind can be the thing that shocks against the surrounding gas, the interstellar medium or ISM. Now, let me emphasize that actually it's a little more complicated. It turns out that there are two shock waves associated with this event. Because whenever a gas compresses and heats up, you can get a shock wave and emission. So what we call the forward shock is, I think, what people would normally call the bow shock itself. That's where the shock wave propagates into the interstellar medium. But there's also what's called a reverse shock, and that is the compression and heating of the wind that came off of the object, in this case, the pulsar wind. Now, this is an artist's rendition of such a structure, and I would say the pulsar wind shock could be thought of as this reddish region inside, and the forward shock or bow shock would be shot as the yellow region. Of course, it's a 3D thing, and you can think of that 3D surface of these two shocks as being separated by a separator or separatrix called the contact discontinuity. Okay, in general, as Tom mentioned, what shocks do is they take supersonic motion and convert them into heat, and that heat causes radiation. That's what lights up, that's what we see. So let's look at these pulsar bow shocks and see how the two kinds of shock waves can light up and talk about those for just a minute. So first, let me focus on the relativistic wind from the pulsar that gets heated and shocked. Well, what happens when that shock wave occurs is that the electrons and positrons get accelerated to relativistic velocities, and as they move in the magnetic field that's embedded in them, they do what's called synchrotron radiation. They let off a glow of radiation, which in these cases, since the electrons are accelerated to enormous energies, higher than the energies that we can actually produce in accelerators on Earth, that synchrotron radiation extends up to the X-ray band or even higher. So when we look with an X-ray telescope, and a great example is the Chandra X-ray Observatory, you can often, if you look at a rapidly rotating, fast-moving pulsar, you can see a bright X-ray glow with a trail behind it. That will be the bow shock, and the trail behind it is left behind electrons and positrons from the shocked pulsar wind. Sometimes you can also see this in radio. The two examples on the left, where you can see a bow shock and the kind of orangish color is in the X-rays. In the blue and red composite, you can see the emission that would occur in the radio band. So that shock wave will have emission extending continuously from the X-ray down through the optical to the radio band. Turns out it shows up most prominently at the top end of the X-rays and most sensitively at the low end of the radio band. But you can see very similar structures in those two ranges. Okay, so that was the shocked pulsar wind. Now, remember what we're looking at is this wind from the spinning neutron star. So when it shocks, it lights up that wind. And what's I think interesting to me is that it lights it up and then illustrates the structure of the pulsar wind itself. And it turns out that's more complicated. It's not just a simple spherical wind coming out the neutron star. Remember, a neutron star is an object that's spinning very fast, and we see the pulses like a lighthouse. That's why we call it a pulsar. But that means the wind that comes off of it knows something about the spin of the neutron star. Typically, there seems to be two components, an equatorial outflow and then polar jets. We can actually see evidence of this in some of these pulsar wind shocks that Chandra has observed. This is from a study that I and some colleagues did a few years ago. And here's one example, a very nearby energetic neutron star, which goes by the nickname of Gaminga. Ask me later if you want to know where that comes from. And what you see here is kind of three trails coming behind it. It turns out we believe that the top and bottom trails are from the polar jet, and that the middle trail is from the crushed equatorial wind. And below you can see an artist rendition showing that. So in this case, the pulsar is flying off to the upper left, and it's flying nearly perpendicular to the axis of those polar jets, which are swept back behind it. The example on the right is similar, but in this case, we're looking at this thing almost at pull on to those polar jets. And so the two polar jets lie close to on top of each other. So we get the kind of disk making a blob at the front and then the polar jets trailing behind. So that's the structure of a shocked relativistic wind from the pulsar. But what about the bow shock itself? Well, the forward shock, the shock against the interstellar medium, that's going to be rather different. That's not this relativistic electron positron plasma. That's normal gas made up of atoms and their associated electrons. So one thing I should emphasize here, we haven't looked at the classical shock waves that many people study, for example, those from supernova remnants, but also those are, slabs of gas being emitted, getting heated, and then radiating as it cools. The thing that's interesting about a bow shock is because it has this kind of arc shape, when you shock the gas, it can flow along that arc and disappear behind it. It can actually move away fast enough that it moves away before it has a chance to cool off, before it has a chance to emit the energy associated with the compression. So these are rather special shocks. They're called non-radiative shocks. And what you're seeing is not just the heat energy of the shock itself, but rather you're seeing a faint tracer of that heat energy from gas particles that jump into the shocked hot region. So bow shocks are kind of unusual. They're very faint in the optical emission when you look at them around these pulsars, but occasionally they can be seen. And this occurs when the shock wave is having the pulsar slamming into neutral gas. Now, why is that? Well, the reason that neutrality is important is that if you think about the interstellar medium, like everything in the universe, it's mostly hydrogen. And hydrogen, as you know, is very simple. It's a proton plus an electron. But if it's ionized hydrogen, that electron has been ripped away, and so you just have a bare proton. A bare proton does not have any associated electron, which can therefore not jump between different energy levels, emitting lines of light. Yes, it can radiate, but it radiates in a continuous way, Bremsstrahlung. Now, if it's neutral gas, that in contrast has an electron associated with the proton, and it can jump around emitting the classical line emission that we see from optically emitting heated gas. So in the right, I have a photograph of an object that we have been studying. It's a millisecond pulsar, a very rapidly rotating neutron star, which is apparently flying through a region of largely neutral interstellar medium. And this photograph taken, well, the white is in continuous light of the background stars, but the red is in the emission line of hydrogen called H alpha, the strongest optical emission line of hydrogen. And you can see this kind of arc-shaped glow of the hydrogen that is being glowing as it drifts into that interstellar medium. Well, there's a few other examples of these, and they're very pretty. I'm showing you, I guess, four more on this slide here. A number these are all photographs that my group has taken typically in the light of this hydrogen emission line. The composite picture on the right shows a hydrogen emission line and one of those X-ray trails coming from that particular pulsar. So I've shown you 5 of these objects, and I think what's kind of interesting to me is that you've actually now seen almost all the ones that are known. After a decade of us searching for these things, we've only found 9 of these objects. 9 of these pulsar emission objects that have H alpha nebula. Well, okay, why is that? Well, that means they're very special. And I think the reason that they're special is probably best traced to the idea is that if you think about the interstellar medium, the gas between the stars, the region that Tom was talking about was kind of special. That's where new stars are swarming. The typical by volume region of the interstellar medium is ionized. So it's relatively rare for there to have one of these pulsars crashing through a largely neutral region and making a shock wave against neutral gas. So that's rare, but they're also super useful. And that is because hydrogen emission, H alpha emission, is a line. It has a particular energy. And that means when you study it, you can measure Doppler shifts. Now, the X-ray emission that we saw from synchrotron nebulae, the shocked pulsar wind, is a continuum. It's beautiful, it's powerful, it's interesting, it's giving the energy of the relativistic gas, but it doesn't tell you about motion. It doesn't tell you about kinematics. In contrast, this bow shock, this forward shock, this H alpha emission, you can actually measure it by measuring the Doppler shifts at different places along the surface and work out the 3D structure of the flow around the gas itself. And the way in which we do this is we do what's called spectral imaging or integral field spectroscopy. We have a thing where we take a spectrum at every given point across the image. And here's an example where a couple of these pulsar bow shocks you can see as a function of the velocity relative to Earth, the shape of the shock differs. That's great because with some careful calculations, you can use it to figure out lots of things about the pulsar and its wind and about the shock wave motion through the interstellar medium. I'm going to close by mentioning one more aspect of these, which I think is particularly interesting that I and my group have been focusing on the last year or two. And that is that occasionally these pulsar bow shocks do something really weird. Now, as I say, there's not that many of them known, only 9 of them show up in H alpha. But of the ones that show up in H alpha, several show an additional peculiar property. The photograph that you see on the right, or the composite image you see on the right, is made up of two sets of images, which we took. One is with the Hubble Space Telescope in this line of hydrogen H alpha. I don't know if you can see my little arrow cursor, but what I'm outlining here is a shape that Jim Cordes of a shockwave that Jim Cordes and I discovered about 30 odd years ago now, which has come to be called the Guitar Nebula. It's supposed to look something like a guitar in space. There's a pulsar at the very tip of the head of the guitar, and it's flying along to the upper left at a very high velocity, over 1,000 kilometers a second. Now, the bright spot at the beginning in the red, remember H alpha is being shown here in this blue image from the Hubble Space Telescope. Red is showing an X-ray image from the Chandra X-ray Observatory. And you can see there's something peculiar going on. There's a bright spot at the front, that's the bow shock and the pulsar. But there's also this kind of line of X-ray emission going off a little bit to the left, mostly to the right. And that line is moving in a direction that doesn't seem to have anything to do with the motion of the star, which is flying to the upper left through space. We call these things X-ray filaments, and what we believe they are relativistic particles escaping from the bow shock, jumping onto a field line of the surrounding interstellar medium and flying along that field line, radiating synchrotron radiation as they go. So those are peculiar, and I and a graduate student are trying to understand the physics of how that occurs, and we can talk about that more later if possible. So here's the last object I'm going to show you before I wrap it up. Here's another bow shock that we found, and this is a neat example because it's got all the ingredients I've discussed all in one object. Over on the left, here's a composite image again. In red now is an H alpha image, actually taken with a ground-based telescope with the Gemini Observatory. And in blue, in this case, we show the X-rays. So if you look in blue, you can see at the tip of the box there's a pulsar flying along and a trail behind it of that shocked pulsar wind. Then if you zero in on the H alpha emission, you can see one of these beautiful colored bow shocks with this, in this case, very peculiar, almost helix looking interior of the shocked X-rays inside of it. And then very faintly, heading off in a random direction, is this filament of electrons and positrons at super high energy propagating through the interstellar medium. Beautiful, not completely yet understood, but I think an exciting way of understanding high energy particles and how they propagate through the galaxy. So here's my wrap up before I turn it on to our last speaker. Remember, what bow shocks do is they trace the impact of a supersonic object against the surrounding medium. And typically in astrophysics, the impacting stuff is a wind or a magnetic field. Pulsars are fast and they have strong winds, so they should make bow shocks. Now, we quite often, and in fact, see 100 plus examples of the bow shocks in the X-rays where we see the shock reverse shock of the pulsar wind. Chandra observes many of these. Very occasionally, we can see the forward shock, the bow shock itself. It's usually invisible, but occasionally when you hit neutral ISM, we see an H alpha bow shock. And they're pretty, and I think I've argued that they can teach you a lot, but I think it's time for me to stop and pass it on to our next speaker.
Thank you, Roger. Phil, the floor is yours.
Thank you. Okay, let me just start from the current slide. Okay, so hopefully you can see this. Yeah, so my name's Phil Appleton. I'm at IPAC at Caltech, and I'm going to talk to you about shocks on a very, very different scale, on a hugely different scale, where it's very difficult to see the individual kind of features that we've seen from Tom and Roger's talk. But we know that they're present in these large-scale systems. So first of all, I want you to get to know the Stephan's quintet system, which I'm going to talk about. It's a compact group of really 4 large galaxies, even though it's a quintet. The 5th one is in the foreground, and it's about 300 million light years away. One of the 4 is an intruder. We call it the intruder. It's crashing into the rest of the group at a gigantic 1,000 kilometers per second, which is about 2 million miles per hour. So if there's any gas in that group, as that galaxy plows into it, it's going to produce shock waves. And in fact, it will produce a large-scale shock wave, and then behind it, we're going to see that there are all kinds of consequences due to turbulence behind that main shock wave. So this talk is about trying to use new space-based observations to study the effects of shocks on large scales and turbulence on an intergalactic scale, so even bigger than galaxies. And what we've been looking at before in the previous speakers are on tiny, tiny scales, whereas we're looking at scales of galaxy size and even bigger, and trying to understand how this intergalactic gas maybe help us understand the formation of the first galaxies, which are probably turbulently dominated. So let's start by, first of all, getting to know a little bit the quintet. So we'll ignore this foreground galaxy here. This is a beautiful NORCAM image from JWST. And there's really 4 galaxies in a row. They're almost in a chain. And the intruder is this one here, a spiral galaxy it's coming towards us at about 1,000 kilometers per second compared with the group. And it's crashing into the group. And as we'll see, there is a large-scale shock that's created, which we know it's there. We don't have enough resolution. We don't have this beautiful resolution and detail to be able to see the actual details of the shock. But what we see is the consequences of the shock. As the shock has passed through this gas that's in the group, and the intruder is smashing into it, and ahead of it, you get this hot gas that's been heated to millions of degrees as a result of the shock. And that's the first indication of this very, very strong shock from the intruder plowing into the gas. And that all seems very well, and we don't have enough resolution in the X-ray to really see the details of the shock. And it's also in 3 dimensions. A lot of it is coming towards us, which makes it even more difficult. But in 2006, we discovered, okay, let me just see if I can get rid of that. Yeah, I hope you can still see the top part. So in 2006 with Spitzer, we actually really were surprised to see that the entire shock front of this X-ray shock is emitting lots of infrared emission from rotating H2 molecules. And H2 molecules are very fragile. And if you heat them up too much, they break apart. So how can so much of the energy be coming out in these rotating molecules? And the blue light here that we're seeing is from these molecules. And with Spitzer, we had the Spitzer Space Telescope didn't have very good resolution, but now with JWST, okay, there it is. We can now see the same picture, but now we see it in much greater detail. And you can see that there's all kinds of clumps and things going on in this. And what we're seeing is emission from hydrogen molecules. And this, we've modeled the actual excitation of this gas back in the Spitzer days, and we know that it has to be shock heated. There's virtually nothing else that can heat it, but they have to be low velocity shocks, not the high velocity shocks of the 1,000 kilometers per second. So the discovery of the hydrogen molecule was a puzzle, but it's also an opportunity to understand what happens in the wake of a big shock when you have molecular material that can even form, and there may be pre-existing material that is running into the hot gas, and what happens what happens in those situations. So how are these molecules formed? We can use them to map out regions where the energy in the shock, we know a lot of energy is coming out in these rotational H2 molecules. It's been radiated away, so it gives us an opportunity to study the effects of turbulence in the wake of the main shock. And also we can also use the hydrogen molecule to look at how the molecules are moving through the Doppler effect, because even though we can't resolve the individual, probably small shocks that we know are present to actually heat the gas, because it's heated up to several hundred to up to 1,000 degrees in the molecules, and that has to be produced by shocks. but we can actually use the Doppler effect to actually study the kinematics and try to see what's going on in a bit more detail. So that's what we've been doing with the James Webb. So what do we learn from taking a spectrum? So on the left, I show you a spectrum of this molecular gas in Stephan's quintet, taken actually with the IRS spectrum on Spitzer many years ago. And one of the remarkable things, if you're an expert at looking at infrared spectra of galaxies, you will see this doesn't look like any normal galaxy whatsoever, because it's totally dominated by these emission lines, which are regions where the molecules are spinning very fast and they emit at certain wavelengths. So at 28 microns, 17 microns, 12 microns, there's a whole rail of them. And the whole spectrum is dominated by molecular hydrogen. And there's very little emission from other places. There is some silicon-2 emission, which also we think is coming from shocks. We've been able to model that too. But if we zoom in on one of these lines, we can actually look at the Doppler effects, the motions in the gas. So this is actually a James Webb spectrum of one of these regions. And it's very typical of what we see all the way along the main shock front. We see lots of gas. So let me explain what this is. We have the emission from the rotating molecule, which has been heated by shocks. And then in this direction, we have the velocity, which we get from the Doppler effect. Now, Stephan's quintet, because of the expanding universe, the whole of Stephan's quintet is moving away from us at about 6,000 kilometers per second, or just over. And in fact, the intruder galaxy is at about 6,000 kilometers per second. So we see a lot of molecular hydrogen piled up at the velocity of this intruder that's plowing in to the gas. We also see a little bit of emission at the very highest velocity, which is the velocity of the group itself. But interestingly, we see a lot of gas in between and this gas has to have been decelerated. So when the intruder hits, the gas in the intruder is being decelerated through lots of shocks into the into velocities that really there shouldn't be any gas in there. And this decelerated gas is telling us that the shocks have shocked the gas and slowed it down into this intermediate velocity region. We also see another interesting effect that we're trying to understand. We think we sort of have a pretty good understanding of what's going on. But we actually can, not only do we detect the molecular hydrogen, but we can actually measure the temperature of the molecular hydrogen. I don't have time to go into how we do this. But what we find is if we focus on this red curve, that was similar to the previous one I showed, with the peak at the intruder velocity, and then this is some gas at the group velocity, and then you see gas that's been sort of decelerated into the intermediate region. What we see is a progression where the coolest molecular hydrogen is much closer to the intruder velocity, and then we see warmer molecular hydrogen that's been shifted, it's been decelerated more, and then we see ionized gas, which those are some of the other lines I saw. This is particularly ionized neon, is also shifted, but shifted even more. And then finally, ion emission, which is also an ionized ion, is shifted even more. And most of the gas in this ionized gas is lying in the in-between regions. So we see this successive deceleration depending on the temperature of the material and how highly excited it is. And this is symptomatic of basically gas that's depending on the density of the gas. The lower density gas would be more strongly decelerated than the denser gas. And so it makes sense that the cooler molecular hydrogen would be less decelerated. But our picture of what we think is going on is sort of just to try and bring it in a little bit into the previous speakers, is that you have these molecular clouds. Well, first of all, you have a main shock that passes through the group gas and heats it up to millions of degrees. But coming behind that are clumps within the intruder, which are experiencing essentially a flow over them due to the fact that this gas that they're running into as being sort of heated by the main shock. And so you end up with something like this, a picture. It seems a little complicated, but you have a flow of group-wide gas coming in, and this gas is hot. And you have some sort of a bow shock probably. And then behind it in the classical picture, like in a supernova bow shock, you just have a shock, you'd have a shock that passes through the cloud. But what we think is going on is that these are fuzzy molecular clumps. And when you make numerical models, like computer simulations of what happens when you flow a hot gas over a molecular cloud, it doesn't behave like a very simple classical thing like we've seen. It doesn't behave like this immutable object that just produces a beautiful classical bow shock and the various shocks. It actually very likely produces a sort of a layer over the cold cloud, which is basically it's a mixing layer where hot gas is getting mixed with the cold gas, and it can actually flow over it, and then some of it gets stripped off into tails. And this is the sort of picture that we're trying to develop to understand what we're seeing. And the lower density gas gets accelerated into these tails, and we end up with the clouds can actually survive through this very, very nasty environment where you have this 1,000,000-degree gas flowing over them. You know, there's all kinds of instabilities that happen in molecular clouds that would tend to destroy them. But we think that this layer can build up on the surface. And that's where lots of little low velocity shocks are being created that are producing the energy that we see in the mid-infrared H2 lines. And then gas is being extruded off it and accelerated into the tail. And if you look at a deep picture of the molecular hydrogen, this is a 7.7 micron image, which actually includes something called pars, which I'll ignore for the moment because they're extremely weak in the main shock. But what you can see is you see evidence of these sort of head-tail structures. And here's a beautiful example where you might even have a real bow shock there in front of this with turbulence behind it. But all of these molecular clouds are experiencing the sort of influence of the flow of this hot gas that was heated by the main shock as the clouds from the intruder are being sort of excited and heated in this way. And so, you know, that's what we're seeing is basically turbulence in action. And understanding this kind of turbulence, the problem is that a lot of the models of molecular clouds in these fast flows are very primitive. And especially when you come to very supersonic, essentially it's supersonic turbulence, and the models are really in their infancy. But we think that this data can help us understand how molecular clouds can potentially survive in these environments. And if we look at higher redshift, this is the spiderweb cluster at a redshift of 2.1. So this is looking back in time to a much earlier time. This is around the epoch where most of the star formation in the universe was occurring. And here is a supercluster of galaxies. And there's a huge reservoir of molecular hydrogen here sitting in this group. And you can see almost a chain of objects, a bit like Stephan's quintet, in this system. This is the so-called spiderweb cluster. And so understanding what's happening in the more nearby system of Stephan's quintet can maybe help us understand how these reservoirs of molecular hydrogen can survive at higher redshifts, and maybe even higher redshifts. And James Webb is pushing out to very, very high redshifts. So in summary, Stephan's quintet contains a giant shock front composed of very hot X-ray emitting gas, cold and warm molecules along an interface with the fast moving intruder. And our spectroscopic observations with the MIRI spectrometer show us that the molecular gas is strongly heated, and much of the warm heated molecules is at the same velocity as the intruder, but some of it's decelerated in the collision. And we can try to understand how the molecules survive if we look at how a cold clump experiences a flow of intergroup gas over it, which heats the surface of the clouds, strips some of the material off, and the interior of the cloud may be protected by this layer in such that it can actually survive for much longer than a simple cloud crossing time in a simple ballistic picture of a cloud with a bow shock and then a cloud shock inside the cloud. And so we think that this helps us understand how this molecular gas can stick around for such a long time, because it really should disappear very, very quickly. It would be destroyed very quickly, but it can be recycled through this mixing layer on the surfaces of the clouds. And that's what we're trying to understand at the moment in our team. Thank you.
Thank you very much, Phil. We have some time for questions, so please drop them in the chat. I'm going to talk about the additional resources after the question. So the first question, I think it's for Roger. Where does the mass come from in a rapidly moving neutron star, as it probably isn't the neutrons?
Good question. It's not the neutrons. In fact, it's not much mass. It's almost pure energy. It turns out that what you have here, a neutron star is like, it's a solar mass worth of stuff in a city-sized ball, but it's spinning super fast. It's a flywheel that has enormous energy. As it spins down, that energy produces, basically out of nothing, out of pure energy, you make electron-positron, matter-antimatter pairs. Not very much of it, but each particle has so much energy that when it flies out in that wind, it has a lot of momentum. And when it slams into the interstellar medium, which is relatively dense, it can still hold that off in a bow shock. So nope, it's not the neutrons. It's not even stuff from the neutron star itself. It's pure energy generated from the spin power.
Thank you. There's another question. I think the three of you can reply to it. How is the velocity of the bow waves, bow shocks, measured?
Okay, the velocity of the bow shocks are measured when, in fact, the velocity of the neutron star we can measure by seeing it march across the sky. If you know its distance and you know its angular velocity, you can figure out how fast it is. So that's how we figure out the speed of the thing. But the velocity of the gas in the flow, I think that's one of the things I was trying to emphasize. When it's the X-rays, the shock pulsar wind itself, you can't do that because X-rays are smooth, they're continuous. But when the hydrogen from the interstellar medium hits it, hydrogen is an emission line. And by measuring the wavelength of that emission line, whether it's red shifted or blue shifted, you can measure the velocity of the flow around the surface. So it's these special rare cases where you see that hydrogen glow, those let you measure the velocity of the bow shock flow.
Thank you. Tom, Phil, do you want to add anything?
Yes, I do. In the case of stars, however, I mean, those stars that you saw are much, much nearer than many of those pulsars. And what we can do is with James Webb over something like a year or 2 years, actually measure the motion of the gas outwards. So as Roger was talking about the Doppler shift, that's the motion towards you or away from you. But in addition to measuring that, which of course we can do from lines in the same way that Roger mentioned, we can also actually see the material moving outwards at right angles to the line of sight. So combining these together, we get a really nice 3D picture of what's happening in a bow shock from a young star.
Yeah, and I would just add that coming back to Roger's point about the X-rays, the X-ray spectroscopy is now becoming able to, at some level, resolve actual lines in the ion emission, in the X-ray emission, some of the X-ray lines, and in principle, you probably at some point in the future would be able to measure the flow of the X-ray gas over those bow shocks. Don't you think, Roger, that's potentially
In this
possible?
case, no, because it's synchrotron emission from the
Oh,
relativistic
yeah, in
pulsar
your
wind,
case.
so no
Yeah, in your
atoms.
case, yeah. But I think in the case of Stefan's quintet, for example, there you have the hot X-ray gas that's, is in the wake of the main shock, and that gas is moving, and it may be a three-dimensional flow. We're looking at it almost face on. You may be able to see motions in as you move away from the center to the outer parts, you may see a shift in the ion lines or whatever lines are mainly present in the X-rays. But at the moment, we don't have that resolution to be able to do that.
Actually,
Thank,
CRISM can do that. We have a new
Oh,
X-ray telescope that does
oh,
have the
yeah,
spectral resolution to do that.
yeah. Okay, well, that's a proposal.
okay. Question for Phil. It appears that the intruder is in a fight with another for material. I'm just curious what you think may be the ultimate result
Yeah.
of this interaction.
Yes, that's a very good question. I mean, the other galaxies in the system are almost likely to merge in the next 500 million years or so. It's not quite clear what will happen with the intruder. The intruder is moving very quickly, but of course, it probably has a dark matter halo. Well, I'm sure it does. And so there is something called dynamical friction, where the galaxy is slowed down because it has this massive halo. And I think ultimately, if you go far enough into the future, you will end up with a giant elliptical galaxy composed of the remnants of these galaxies. And we're seeing them already at a point where a lot of the gas has been stripped out of the galaxies, very little gas in the actual galaxies themselves. So a lot of things have already happened to these galaxies already in the past. And certainly, if you go far into the future, they're most likely going to end up as a giant elliptical galaxy. Good question.
Interesting. Tom, another question. Do all stars form Herbig-Haro objects?
Yes, it does seem that they do. And just to mention everybody what a Herbig-Haro object is, it's essentially a shock. We talked about shocks radiating energy, and so in star formation regions, when a shock occurs, it actually radiates a lot of the energy behind it. That's not necessarily true in some of the galaxies where you get, for example, synchrotron emission. That's already been mentioned by Phil and by Roger. In the case of young stars, however, it's quite rapidly radiated away, and so whether it's even a brown dwarf, which is almost a failed star that's forming, or we have a star similar mass to the sun, or we even go to even more massive stars, we see in every case Herbig-Haro objects, and they're essentially just the cooling regions of those shocks that we talked about.
Thank you, Roger. There are three questions for you, and we only have 2 minutes left. I'm going to read them very quickly. When Jocelyn Bell Burnell was first studying pulsars, was this possibility of pulsar bow shocks imagined?
I think the answer is probably no, but remember, the discovery of pulsars was an amazing surprise, and they've continued to give us amazing results over the intervening 50 years. They do wonderful things, and many of them we have not been imaginative enough to predict ahead of time.
Thank you. When and how did this idea of the bow shocks applied to pulsars develop?
Well, we saw them. I mean, like I said, we didn't. I think in principle, people thought such a thing might exist, but when we first measured them, I think that's when we started to focus on it. Originally, the synchrotron X-ray trails behind the pulsars were seen, but the idea that there could be a bow shock visible in front of it was actually a little bit surprising. The first photograph that I showed you is the first one discovered, and you see this kind of very beautiful glowing arc shape that goes around the front of the pulsar. And of course, you say, "Oh, it's a bow shock. Now we need to understand it."
Thank you. Last one. Does the discovery of only 9 pulsar bow shocks so far mean another approach to detection might discover more of them? And if so, what might that be?
Ooh, if I knew what it was, I would have found more. I've looked at hundreds of these things. Now, I think as I argued, they're rare because they have to have the special case of flying through nearly neutral interstellar medium. And it also has to be a very energetic pulsar. Several thousand pulsars known. Of the few hundred most energetic, those are the ones that make these X-ray trails. And of those, as I say, there's about 10%, 10-ish out of a few hundred, those are the ones that had the bow shocks. That's not crazy because that's when the fraction that is probably going through neutral gas. But, I think at some level they do exist around many more. And if the questioner has a great idea on how to pull that out and find them, I would be delighted to hear it. It's been a challenge.
Thank you very much. I don't want to keep more of your time here, so I will just briefly explain what additional resources are for our audience. And Amelia, do you have the slides there by any chance? Otherwise, I'll share my screen. Okay, there they are. Okay, so we have some resources on NASA's Universe of Learning about stars, stellar evolution in general. We have program guides, we have the Cosmic Canvas, which contains activities that are art-based, and we also have videos about stellar evolution on view space. We also have, I'm so sorry, other resources that explain Herbig-Haro objects. So if we can go to slide 44. There is, I'm not sure if this is moving. Is it me? Or I'm not seeing what's happening. Apologies for that.
Sorry, I don't know why it's not sharing at the moment.
Oh, okay. Well, we also have resources on Herbig-Haro objects. We have an image tour, and we have more resources about pulsars and bow shocks in the slides. And we also have many activities and resources about the Stefan's Quintet. So I invite you all to check the resources on the slides. And also we have a Word document that has compiled even more resources for your events. I want to thank our speakers because I kept you for 2 extra minutes. And thank you very much for joining us today.
Thank you.
Thank you.